All right, first a few announcements. Homework 6 is out. It is due on Sunday, so keep that in mind. It's on a slightly unusual date. This is so that you have some time to review the solutions to the problems, which will be posted on Sunday at 10:05 p.m. or something like that. So you can take a look at them. And remember, we have a relaxed grading scheme for this homework. Any attempt will get you 100%, but as usual, attempt them honestly. It will help you a lot in the exam. And exam 3 is December 6th, Tuesday in Ackerman Grand Ballroom, 8 to 10 a.m. And it's only lectures 15 through 20. Okay, so department context-free grammar, Rice's theorem, and quantum computing parts. I will also add more practice problems on the quantum computing part, the last 3 lectures to homework 6 today and tomorrow, so you can also work through them just kind of as a preparation for the exam. All right, and exam 2 grades. I know we are kind of overdue by about a week already, but I'll have them ready by the end of the week. All right. Any questions about the logistics? And as usual, you'll have time to ask for regrades and etc. on exam 2 and exam 3 as well once they're out. Any questions? Yeah.
What do you expect would be a realistic turnaround time to expect on exam 3? A couple of weeks?
Yeah, at least maybe a couple of weeks, I would say.
Maybe. I know they extended grade deadline to the 31st.
Mm-hmm. Yeah. Yeah, so I had to get everything, so it's going to be a couple of weeks. All right. Okay, so if there are no other questions, let's get started with our last lecture. We have a lot of ground to cover. So, we'll take it slow, but we'll also kind of be on a little bit of a rush, but hopefully it's fine. So last class, we did a lot of things. First, we did our first non-trivial, we saw our first non-trivial quantum solution, right? There are some problem. It's not necessarily exactly something that a computer scientist would like to solve, but it's kind of computational, I think. You're trying to detect something with using a box, counting the number of boxes, and so on. And we saw a solution which was, which was non-trivial because we were using the laws of quantum mechanics, right? We were doing this rotation, and sending it through, bringing the photon back, sending it through, and so on, right? We could detect whether or not there was a bomb, with the chance of exploding being minuscule. If you're in the classical world, if you're not using quantum mechanics, that is not possible. Okay, that's our first demonstration of the non-trivial use of quantum laws for our advantage. Okay, and we also saw what gates are, kind of just hinted at what they are. And then we went from single qubit systems, which are just like 2 numbers describing the system, to multi-qubit systems. Okay. So what we'll do today is talk about gates on 1 qubit, 2 qubit, 3 qubits, and then we'll kind of look at a circuit and then define quantum circuits and quantum computers. Okay. So at the end of the day, you should all be set for going home and building up your quantum computer in your garage. All right. Okay. So let's get started. So just as a recap, we had multi-qubit systems, right? We said if you have 2 qubits, basically think of them as photons. They are in some joint system. This is my best illustration of 2 photon system. Then this will be described by 4 numbers, right? And we said we'll use Dirac's Ket notation, which kind of makes things a little bit more streamlined. So the system, the state, is described by something like this. So this 0, 0 kind of corresponds to saying, okay, the photon 1 is in state 0, photon 2 is in state 0, and so on. But you should never think, okay, it is actually in state 0. This is just our English way of saying, because if you start interpreting it as actually in state 0, then you'll get the wrong answer. Okay. the right way to say it in English is the state has amplitude alpha 0, 0 in 0, 0, amplitude alpha 1, 0 on 1, 0, and so forth. Okay, you should think in terms of amplitudes. If you work with amplitudes always, most natural things go through. If you start talking about probabilities, most natural things will fail. Okay, all right. So that's what a multi-qubit system is. Now we have to talk about gates, the kind of operations you can perform on these systems. And towards the end of last lecture, I said a gate is a linear transformation any linear transformation that preserves lengths. Okay, and so concretely, if I have some linear transformation from like d-dimensional vectors to d-dimensional vectors, the property we want is that for all vectors v, the length of v be the same as the length of uv. Okay, so this maps from one set of one vector to another. First of all, it has to be a linear transformation, and the lengths have to be preserved. Okay, I mean, we don't have to work in this abstract sense. We'll only see 3, 4 examples, and those are the only ones that we care about. But it helps to keep this bigger picture in mind. Okay, and nature allows this amazing power that you pick your favorite linear transformation, as long as it preserves length, we can build a device. There is a device which actually performs this transformation. And you can send a system, set of photons through it. There is this device which operates on it and comes out in the resulting state. Okay, and that's the amazing power we are given, and let's see how we will use it. Okay, but let's first understand what this power is by some examples. Okay, so let me say the first few examples will be really classical, but kind of they are useful even in the quantum setting, and also helps us understand this notation and everything better. So example gate 1 is what you can think of it as the analog of NOT gate. Okay, so what is mean by saying NOT? So the gate I'm going to define as follows. Remember, it transforms one vector to another vector, right? So basically, we'll write it as something like this. You have some photon. It's a gate that operates only on a single qubit. I send this photon through, and you get something else out. Okay, so I'm sending the photon through this gate device, and another the same photon comes out in a different state. Okay, but what state goes in and what state comes out? If I send in something in state 0, what do you expect should happen? Get state 1. If I send in something in state 1, what do you expect should happen? State 0. Okay. Now, I mean, this is kind of what you think a NOT standard NOT operation is, right? You send in bit 0, it becomes bit 1. Send in bit 1, it becomes bit 0. But remember the first law of quantum mechanics. There are 2 possibilities. The state can be a superposition of these things, right? So what if I send in a photon which is in state alpha times 0 plus beta times 1? What would the new state be? So, the photon I'm sending in here is in this state. What would I get out here? Again, your natural guess will work. So what could be one guess? Yeah.
Is it like 1 with probability alpha squared?
So devices are deterministic, right? Gates are deterministic, they just transform. So only when we measure do we see collapses and probabilities. Until we measure, kind of everything is natural, I would say. Yeah.
Beta times 0 alpha.
Exactly, right? You should think linearly, right? Everything is linear. I have a system as amplitude alpha on 0, amplitude beta on 1. Okay, then you can think, I have amplitude alpha on 0, it goes through naught, it becomes 1. And amplitude beta on 1, it goes through, it becomes 0. Okay, so as long as you're working with amplitudes, this sort of linear logic is perfectly fine. Okay, so once I define what the gate does on kind of the basis states like 0, 1, and so on, I can extend it to general states by linearity. Yeah.
You keep saying as long as you're working with amplitudes as opposed to probabilities, but what is the difference?
Like basically, you should not do this if you're doing measurements. Okay, so as a warning, never do this if you're doing measurements. Okay, so that's why the way we are going to define circuits, we'll only do the measurements at the very end. Okay, there's this thing called deferred measurement principle, which says that if you're doing any measurements, you can do them at the very end, but it makes everything so much nicer. Okay, so I'm going to completely skip that step and say all the measurements will be done at the very end. Okay, so that makes everything nicer, right? So by linearity kind of extension, you should expect this to be okay. So if you think of it as vectors, that is what is happening formally here. I have my photon in state alpha beta. It goes through naught and comes out in a different state. And what is this new vector state? Beta and alpha. Okay, so the NOT gate is basically swapping the two coordinates. Okay, and there's a different way to visualize this. I can also write this action as a matrix vector product. Okay, this is something you can check. If I multiply this matrix 0, 1, 1, 0 with the vector alpha beta and follow the rules of matrix vector multiplication, like when you multiply 0, 1 with alpha beta, then it swaps, so you get beta and alpha. Okay, so there are different ways of visualizing the gate. You can think of it as I'm going to define what it does in the basis vectors, and then extend it to all states by using this kind of linearity. If I have amplitude alpha, then whatever happened on 0, that kind of gets added up to amplitude beta, and whatever happened on state 1, and so on, right? You can also visualize it in this vector operation world as a matrix times a vector. Okay, these are all equivalent. For our purposes, they don't make too much of a difference, but when you want to go deeper in quantum mechanics or quantum computing, you have to deal with matrices. Okay, but to define things, we don't need them. All right. Okay, so that's the NOT gate, and clearly, it's a transformation that preserves lengths, right? I'm just swapping the two coordinates, so the length of one vector is the same as the length from the NOT. So it's kind of a sanity check that it is indeed a valid gate. Any questions about this? We'll do 3 more examples to kind of get our heads around this notion. Example number 2. And this is probably the most important example. And we saw this already, is Hadamard gate. This was a transformation which reflected every state above the line with angle 22.5 degrees. Okay, so we can think of this again in very different senses. So geometrically, if you have a state alpha beta, then the Hadamard gate corresponds to reflection about line with angle 22.5 degrees. Okay, so let me draw a consistent picture. You have your photon. I'm sending it through the Hadamard gate, which is denoted with the H. And I get the same photon, but in a different state. Okay, and what is this new state? I can describe it by action on the basis vectors. We have a geometric description too, by action on the matrix viewpoint and so on. So let's do both. So if I send in 0, what do I get out? The Hadamard gate's operation is you get out the plus vector. Okay, so if I'm reflecting 0 at the 22.5 degree angle, I get at 45 degrees, which is exactly 1 over square root 2. Okay, if I send in 1, I get 1 over square root 2 times 0 minus 1 over square root 2 times 1. Okay, we can take this as a definition of Hadamard gate. It transforms 0 to 1 over square root 2 times 0 plus 1 over square root 2 times 1 to this. Then once again, once we define it for all basis vectors, we can generalize it to other things, right? So if I send in a general state, alpha times 0 plus beta times 1, what should I get? It's basically you should multiply these two things with first line with alpha, the second line with beta, and add them. All right. So it's going to be alpha times 1 over square root 2, 0 plus 1 over square root 2 times 1 plus beta times I can simplify this a little bit and write this in a more clean way as okay. Once again, you can verify that this is a transformation that preserves length. It's kind of clear from the geometric viewpoint, but you can also numerically check it if you so wish. Right? And how about the vector viewpoint? So what's happening here? If I send in the vector alpha and beta, I'm getting out the vector. Okay. But if you think of the state as a two-dimensional vector, as two numbers, then the transformation is you'd have alpha beta goes in. What comes out is alpha plus beta over square root 2. And second coordinate is alpha minus beta over square root 2. Okay. And we can also check again that this is a matrix vector product. Okay. So you can go once again by basis vectors or just this matrix description. So the Hadamard gate kind of corresponds to this matrix. Any questions? Okay, let me do a quick, summary of what we learned. So there are two ways to describe gates. The first is, tell what happens on basis states. If you have a single qubit, then the basis states are just 0 and 1. If you have two qubits, and the basis states are 0, 0, 0, 1, 1, 0, 1, 1, all of those things. Just tell what happens on all of those four vectors, four things, and then you extend to general states by kind of linearity. Okay. The other one is to write down the matrix describing the transformation. Okay, you can do it basis by basis vector, or you can just write down this matrix. Yeah.
Is that matrix the same as like the composition of what happens before the basis vector?
Yes, like you can take those columns and you're just putting them, stacking them side by side. I would say, when you're doing it a single gate, both of them are equivalent, but the matrix really makes things simpler when you compose gates. Okay, when you're composing, you don't want to keep track of everything, one after the other, whereas matrix multiplication is something that's much easier. But again, as I said, we're doing something, we're working on with 2 or 3 qubit gates, so we should be fine for the time being. Okay. All right. And let me also say as a remark, not every matrix corresponds to a gate, right? We need the gate to be length preserved, which is a pretty strong condition. Why do we need it to be length preserving? Well, that's what nature allows us to do. It doesn't allow us to do arbitrary, transformations. Has this weird geometry that you have to preserve lengths. If so, then you can get a device for it. Okay, but the most part, I'd say don't worry about checking whether gates are valid for us, because we only deal with a few. We only deal with a few building blocks, which will all be united. And the nice thing about preserving length, that's kind of one of the nicest, maybe that's why nature also allows us, is that you preserve length once, and you apply the gate again, you have preserved the length again, right? So composing gates kind of, it's still, you're in the same realm of unitary transformations. Okay. Any questions? Okay, these are gates that are operating still on single qubits. Okay, but they keep saying single qubits are powerful, but we need to handle multiple qubits. Right? So how about gates on multiple qubits? What are they? How do you, what do they mean? How do they operate? What do they do? Okay. And so for this, we need to ask, what do I mean by multiple qubits? Again, let's stick to 2 qubits. We'll look at a few examples, and then I'll say something for 3 qubits, and that will be it. Okay. So 2-qubit system is something like, you should imagine we have, I think I had one good diagram. So let me just copy that. So imagine you have 2 photons, right? And they are in a system together. Okay. And you want to perform operations, kind of devices which work on both of them together, right? So the first, there are many questions to ask here. So what is the joint state? If I have 1 qubit, then we know it can be in a superposition of 0 and 1. If you have 2 qubits, then we know this joint state is something like right. So you have 4 possibilities. So the state is described by superposition of these 4 things. Okay. And then we need to ask, what if you apply a gate? So let's do some examples. The easy case I would say is you have a joint system, but your gate still only operates on 1 photon. Okay. There are more complicated things where the gate can function on both of them together. But first, let's figure out the arithmetic for what happens when you have a single, like the gate applies only on a single one, right? So example number 3 is and the way we will denote it is I'm just going to draw these wires really. Again, this is all just our pictorial notation. It doesn't really correspond to actual physical realization. It's not as easy in the quantum space. Okay. Suppose I have this joint system and I apply a NOT gate on the first one and I send it through, I get a new system. So what would the new system be? What would the new state of the system be? Okay. And I would say the natural guess is the correct one, right? So let's say I have state psi, which is alpha 0 0 times 0 0 plus alpha 1 0 times 1 0. Okay, I have this thing and I'm sending it through. What should the new state after the transformation be? Any guesses? Intuitively, you would say, okay, the gate is doing nothing to the second photon, right? So does it mean the second photon just goes through? Well, it's not so clear, right? Because your original state is a superposition of the 2 things, right? So they're somehow coupled together. So how would I work out what the new state would be? Any guesses? Yeah. Yeah, exactly. Right. So you would again think what happens for the basis states, right? So I would say, if I were to say describe the state psi in words, what would I say? Something like, okay, with amplitude alpha 0, 0. Photon 1 is in state 0. Photon 2 is in state 0. Okay, this is kind of the joint. If I were to describe the state without using any words, that's what I would do. Okay, so this would be with amplitude alpha 1, 0, the first photon is in state 1, second one is in state 0. With amplitude 0, 1, the first photon is in state 0, the second one is state 1. Amplitude alpha 1, 1, both are in states 1 and 1. Okay, and now if you're applying the gate not on the first photon, what would happen? You would say, the first photon would get flipped, the second photon stays the same. Okay, so you would just copy everything. Oops. It's a problem. Okay, so this is one way to numerically do it. Again, I'm just doing it in painful detail for the first few steps so that you kind of see that there is some logic behind it. There's no magical formula that you have to just learn by rote. There is a simple logic behind it. You kind of figure out what's happening on the individual things and then add them. Okay, you can think of it in terms of, okay, alpha 0 is an amplitude, I mean something, then the gate did something, right? And then add these things up. Okay, so the operation would give us, I had the description in words, now I had to just go back and plug it in the language of numbers, right? So alpha 0, 0, I'm in state 1, 0, right? The 1 has been swapped. Alpha 1, 0, I'm in state 0, 1. Okay, so you're just flipping the first bit and the rest of the things are the same. Any questions about this? Yeah? Alpha 1, 0 should go to yeah, sorry, thanks. This should be 0, 0. Yeah, this should be 0, 0, thanks. Right, so we're not changing the second bit, only changing the first bit.
And I assume it's transposable if you were to put a not on the other one.
Yeah, exactly. All right, and let's do the vector version as well once. So what's happening as vectors? You would say, well, my original state corresponded to alpha 0, 0, alpha 1, 0, alpha 0, 1, alpha 1, 1, ascended through I get alpha 1 0 and alpha 0 0, alpha 1 1 and alpha 0. Right, so NOT is basically kind of swapping these two, right? So we can think of this also as a matrix. And what is this matrix? It has a very simple structure. Okay. Again, you can check this numerically, but the matrix viewpoint is not important for us. It's just to tell you that there is something. You can visualize the entire gate as a matrix. And in this case, the matrix would be of dimension 4, right? Because you're operating on 4 numbers. So if you have 3 qubits, the matrix would be of dimension 8, right? 8 numbers, okay? So in general, if you have k qubits, then to write down the matrix, you would need 2 to the k numbers. And there is a, there's a lot of slitting in your algebra that you can use to write down these matrices, but we are not, that's not too important for our discussion today. Any questions? Yeah?
Can you go again why you say like amplitude, like the way that I've been interpreting alpha is more like the magnitude of the vector. How should we interpret it as like an amplitude?
Because it can be signed, right? Magnitude corresponds to length, right, in some sense, but that's not really the length. It's alpha squared plus beta squared that adds up to 1, right? And we should, they can be negative, and that's very important. Okay, I mean, in quantum mechanics, you allow them to be complex numbers, and but for quantum computing, you don't really need it. It does help in some calculations, but you can just stick to real numbers, but you definitely should allow negative numbers. Okay, good question. Any other questions? Yeah? Oh, that's just to, it doesn't really matter what order you write in. I chose this order because then it makes it clearer what happens to gates that only work on the first photon. Okay, so the way I wrote it here, the state of the first photon is changing first, and the state of the second photon is changing next, right? And the state of the second photon is 0 and 0, the first two coordinates, and 1 and 1. Okay, if you do it the other way, the structure of this matrix would be less clear visually. Okay, but for some other operations, it would be nicer to visualize it that way. If the NOT gate was on the second photon, then the other order would make it clearer. Okay. Any other questions? Yeah.
So while not every matrix corresponds to a gate, every gate does correspond to it.
Every gate does correspond to a matrix. And there's a simple check that you can do. If you give me a matrix, I can do a simple check whether or not it corresponds to a gate. But we don't need to discuss that because we're kind of working in the other direction. We have a few gates, and that's all we care about. Okay. All right. So far the examples are looking nice, but let's do a more complicated and genuinely multi-partite, multi-qubit gate. Okay, and well, we'll build it up in 2 steps again, but let's first do actually, let me do maybe, what example was that? Example 3. Okay, I'll do example 4 a little bit shorter. So what happens if I have if I put the Hadamard gate here? Okay, so if you put the Hadamard gate here, the easiest way to figure out what it does is to write down what happens in the basis vectors. Okay, so if I have 0 0, what would I get? Any guesses? But there's also the second photon that kind of tags along, right? So we're saying with amplitude 1, the first photon is in state 0, the second photon is state 0. I apply the Hadamard gate to the first photon. So its state changes, right? So I should really get 1 over square root 2 times 0 plus 1 over square root 2 times 1 for the first photon, whereas the second photon goes straight through. Okay, so the Hadamard gate here is only operating on the first photon. So the second photon is not changing, right? And then you can, just write down all the other possibilities. It's 1, 0, you get whatever the Hadamard gate does on the first photon. Okay. If I have 0, 1, then I just get all right. So I would say, if you apply some sort of natural rules, you will be correct. Like here, the intuition is that the Hadamard gate is only operating on the first photon, so its state changes. The second one is not changing. But you should be careful in how you apply it. I would say stick to like basis vectors, try to work what happens there. Once you know that, if I give you a general state, you would use linearity. Just add them up. The first equation gets multiplied by some number, the second line gets multiplied by some number, just add up all of them. Okay, so it's nice that everything is linear. That's why linear algebra is very critical in understanding quantum computers. Okay, any questions about this? Yeah,
how did you get I understand like the Hadamard gate for the single qubit, but how did you extend it to 2 bits?
Right, so I mean right now the gate itself only operates on 1. Okay, but we're going to build more things later on. So the gate by definition only operates on 1, but you can build multiple gates which can operate on multiple qubits.
I guess I was asking like the mathematical application down here.
Yeah.
If
Okay.
you look at this backwards, it makes sense. Like it's a half chance of being that or that. But like mathematically, it's kind of hard.
No, don't go through chance. So I would say work with amplitudes. So you would say something like, if I'm with amplitude alpha 0, 0, I'm in something state, and then something happens. Okay. Or if you want to be kind of tedious but kind of accurate, then just work out what happens on the basis vectors. All right, and then add them up. So if as vectors, what does this correspond to? And if I have this and I send it through, I get something, some other matrix. You can add up all of these things. I'm going to short circuit some calculations here. I don't want to like bore you with the numerical part, but okay. So if I add up these equations, this is the transformation I get as vectors. All right. You just have to do some accounting, but this is what you will get. And I can also write this as a matrix. Can anyone guess what the matrix is? The matrix is 4 by 4. But what would you expect this matrix to be? Yeah?
corresponding ones so that we multiply it. So like the first one, first one 0, 0 to.
So, I mean, I think you're right, but I would say maybe easier way to describe it is that you would have blocks. Like here, this was the matrix for naught, right? You had 2 blocks of naughts and then zeros, okay? So the same thing would magically happen here. You would get 1 over square root 2, 1 over square root 2. Okay, so this was the matrix for a single H, kind of we get tying it all over. Okay, but again, as I said, this is just arithmetic. You have to work through this, but it's not too important what this matrix is. But we know that we can calculate it. If you give me something, I can find out what happens in the basis vectors, go through these calculations, and tell you the answer. Any questions about this? Yeah. Exactly. Yeah. It'll have be 8, right? It'll have 8 coordinates, so it will be much more complicated. I'll say a few words about the more general setting, but for now, let's just stick to like what we can just calculate by hand, more or less. Okay. All right, let's do one more example. I mean, we'll do several examples actually, but you know, the examples are leading somewhere. It's not just painful practice. The next example is actually a classically interesting gate called C0. Does anyone know what a C0 operation is? It's called the controlled NOT. So basically, if I have 2 bits in the classical world, what it does is let's say I have bit A and bit B, then I send it through the C0 gate, which is denoted as something like this. Okay, this is classic logic design notation for C0. The first bit goes straight through always, but the second bit gets flipped if the first bit is a 1. Okay, so if A equals 0, B goes through. If A equals 1, B gets flipped. Okay, so the one with the dot is called the control bit. Okay, and the one that can get flipped is called the kind of the controlled NOT bit. Okay, so you can write this succinctly as A XOR with B. So if A is 0, then nothing happens. If A is 1, it gets flipped. Okay, right, so that's a classical description. So what should the quantum analog be? Right, so I want to describe what this is. So let me get that here. The reason we're going to define it is because this is a very important operation, as we will see in physics. Okay, so this is the gate I want to describe, but I can tell you it by what happens on basis vectors. Okay, so if I have 0, 0, I send it through, what would you get out? Any guess? 0, 0. If I send 0, 1 through, what would you get out? 1, 0. 1, 1. Okay, and oops, actually. If I send 1, 1, what would I get through? 1, 0. Okay, so once I have this, I can figure out, what the general transformation is, right? I would just add up all of these things and get the transformation.
How does this scale for more bits? Would it's like every pair gets its own gate, like, or?
Yeah, so we'll talk about that in a little bit. Okay, so C naught as vectors. Okay, so let me first say, so C naught operation is alpha 0, 0 times 0, 0 plus alpha 1, 0 times 1, 0 plus alpha 0, 1 times 0, 1 plus alpha 1, 1 times 1, 1 goes to the vector, which is okay, the change is, basically happening here, right? Right, so these parts are different. So as vectors, what's happening? Okay, so if you look at the equation, essentially what the control knot is doing is it's swapping these two operations. These two coordinates, I should say. All right, so I can write this as a matrix again, and the matrix you can numerically check. It still has a nice structure, I think. Okay, so you can think of the control knot as corresponding to this matrix or this intuitive thing that is swapping the second and fourth coordinates. Right, any questions about this? Seems like a very silly, simple operation, right? But I should say, that's the strange thing about nature. One tidbit is that this is a rather tough to implement gate in practice. It's easy to implement Hadamard gate. It's easy to implement all the other things because they're somehow operating on single photons. Control knot mixes the two things. Okay, and to do it physically is very challenging. You have to, the first time it was done was in 1995. First realization was in 1995 after, after quantum computers were introduced, circuits were built, Schrödinger factoring algorithm, and so on. Okay, they use some ion magnetic fields and some other weird stuff to implement C naught on 2 qubits. Okay, so mathematically it's simple. To realize it physically is challenging. Okay. Any questions about this? All right. Okay. So we are at a stage where I think we can kind of push through all of this sort of painful, detailed calculations and use some heuristics to guess what would happen if I start putting these gates together, right? The power of circuits and power of computing is always you have basic blocks, but then you chain them. You apply these operations again and again. Even in our EV bomb solution, we were applying the operation again and again, right? So let's see what happens, if we have some gates here. I would say C naught is our first non-trivial sort of, gate that operates on 2 qubits. It's kind of also practically very true because physically it's pretty hard to implement. You need some super high grade equipment and experiments to do it. Okay, so let's take a 5-minute break, and when we come back, we will look at our first genuine circuit, which puts different gates together, and we'll see something nice happen. Okay. Okay, so let's look at our first non-trivial quantum circuit, and it's a tiny circuit, but I think it's a very important one in physics. Our very first quantum circuit, a simple one, but a nice one. Okay, I'll stop drawing photons now. My drawing skills are deteriorating fast. Just imagine, basically I want a chain applying Hadamard gate on the first photon. It's again 2-qubit system, followed by the control NOT operation. Okay, so you have C0 and then you have Hadamard. And what happens if I send in 2 photons through this? Okay, so circuit is, intuitively, what does it correspond to? It's just what happens when you chain gates one after the other. Okay. Thank you. So for this particular one, I'm not even interested in all the basic things. If you want, you can work through the action of this gate mechanically. But let's see what it does on a particular state as input. So what happens if I send in 2 photons, which are in state 0 and 0, through this circuit? Let's just track its evolution. Okay, so the initial state is 0, 0. And I'm asking, what do you get at the very end? What state is the system of 2 qubits in when it comes out of the circuit? Well, we can see, this is, so let's try and compute it. We will do it one step at a time. Let me kind of think of it as you have time 0, where nothing has happened, time 1, where 1 gate has been applied, and time 2, where the second gate has been applied. Okay, and it helps to kind of think of general quantum circuits also in this way. You're applying gates one after the other. Let's check what happens after each operation, and then you just chain them one after the other. Okay.
When you say when we check what happens to them after each operation, we're not actually checking because we can't observe.
We can't observe. This is just mathematics. Yeah. That's a very good point. This is just our mathematical calculation. The nature is doing these devices. We have no physical, no way to simulate them and so on. We believe not. Anyway, okay. So the starting state, let me put a size 0 on top, is just 0, 0. Right?
When we take in the photons as input, are they always?
This is really a physical thing, right? And there are 2 photons horizontally polarized, and I'm putting it through this.
So every photon that comes in is horizontally polarized?
Yeah, I mean, the gate is always, you have this device, you can send in any photons that you want. I'm just looking at the case where, the 2 things that I'm sending in are in horizontal polarization. Okay, just as one step. If you had to come to the gate, then I have to do this for 0, 1, 1, 0 and everything. But 0, 0 is already pretty close. Okay, so just kind of understand what these circuits are doing. So send this through. What is psi1? And we want to know what is psi1. And finally, what is psi2? Okay. So what is psi1? We kind of already know, right? And if I send in 0, 0, we know exactly what the Hadamard gate does. It changes the first photon state to plus, and the second one kind of goes through. So what is psi1? Well, I mean, okay, so we can think of it. So we have amplitude 1, photon 1 in state 0, photon 2 in state 1, state 0. Okay. So when I send it through the Hadamard gate, what would I get? I would get amplitude 1, photon 1 in state 1 over square root 2 times 0 plus 1 over square root 2 times 1. Photon 2 in state 0. Okay. So this mathematically corresponds to psi1 being 1 over square root 2 amplitude on 0, 0 plus 1 over square root 2 amplitude on 1, 0. Right? You know, this is something we just saw when we described the Hadamard gate. Okay, so far so nice. But now what happens when I do the C0? So we are sending this state through C0, right? Now it's time 2, what happens? Any guesses? Yeah. Exactly, right? And you can again do it, kind of see what happens on each basis vector and use linearity, right? C0 is a reasonably simple thing because 0, 0 goes to 0, 0, as we said, and 1, 0 goes, oops, 1, 0 goes to 1, 1, right? So we just apply that and use linearity. So psi2 would be 1 over square root 2 times 0, 0 plus 1 over square root 2 times 1, 1. Okay. And I think, you know, okay. So this particular thing, this particular state of a 2-qubit system or 2-photon system has a very special significance in physics. It's called a EPR pair, named after Einstein, Podolsky, and Rosen. And they had this great paper back in the 40s. They didn't believe quantum mechanics, and you would get all kinds of weird contradictions. And you know, one of the bases for those contradictions was, or at least counterintuitive things, was the existence of these EPR pairs. Okay, yeah. The first one or the second one? Time 2, yeah. So time 2, so what happens, right? So let's see what happens to 0, 0. So 0, 0 under the control naught will just be 0, 0. Okay, we're using the rules for control naught here. Okay, and if you're in 1, 0, then you go to 1, 1. So we apply linearity and we get what we wanted. No, you know, basically everything kind of, you use linearity every time. All right. So we know what happens on 0, 0. We know what happens on 1, 0. So just add them up with the right amplitude coefficients and you'll get the answer. Okay. And this is called the EPR pair. They kind of introduced it as a challenge for quantum mechanics. It leads to something called spooky action at a distance. And I think, you know, this kind of hints at why implementing C0 is so hard. because maintaining and generating this EPR pair, physicists know is quite tricky. Whereas if you can implement C naught, you can easily get it. Just apply Hadamard and apply C naught, and you get an EPR pair. Okay. And physics, something we are not going to touch upon. There's something called entanglement, which couples the state of the first photon to the second photon. And EPR pair is a very entangled state. Okay, but again, we are just viewing it as an example of gates. All right. Any questions about this sort of work through example? We started with 0, 0. We figured out what happens. You can ask, what happens if I put 0, 1? You just have to do these calculations again. Time 1, time 2, 1, 0. Again, same thing. Sense 4. Yeah. So EPR in physics, they call it EPR pair. This is Einstein, Podolsky, Rosen. Yeah.
Like the phenomenal thing about this is that like two photons are like 100% of the same.
Exactly. Yeah. And I mean, basically, you cannot decouple the two without collapsing, right? The experiment that they had, it's very fun thing, is they said, okay, let's make an EPR pair. And then I'll put 1 photon on Earth and 1 photon on Moon. Okay, and if I measure the 1 photon, then you immediately know the answer for the other photon on Moon. How did they communicate? That was a thought experiment that they were playing. It leads to some things that seem contradictory, but they are not really contradictory. But anyway, that's a debate for another day. That's why we can spooky action at a distance. All right. So from a math perspective, we can always work through these things carefully. But the best way, again, we are not going to do it, but the best way to compute what happens when you do this gates one after the other is to use linear algebra / matrix view. Okay, so we can write psi1 as we had a matrix for H. Right, we had this big matrix. Maybe let me do H2 for 2 cube. Okay, 2 I'm choosing. Okay, let me just say H. Okay, and we also had a matrix for C naught. So if you wanted to compute the matrix for the circuit that we drew, then you can do it by kind of multiplying these matrices. All right, so you can multiply these matrices and chain them together if you wanted. Any questions? All right. The last example of a gate we need will be our familiar kind of quantum analog of the NAND operation. I'll just call it QNAND. Okay, it's kind of slightly different from what you would think of the NAND should do. So remember NAND the gate, it took A and B and output the NOT of the AND of A and B. Okay, so we'll describe the NAND gate as follows. If I take 3 bits A, B, and C, and I send it through NAND or QNAND. I'll first describe it in the classical setting, and then we will extend it to general things. So this is my diagram for it. I didn't find a standard picture, so this is how I'm going to draw it. The first bit goes straight through. The second bit goes straight through, but the third bit becomes C XORed with NAND of A, okay. So if the third bit is 0, kind of you're just encoding the NAND in the third coordinate. If the third bit is 1, then you're kind of really writing the NOT of the NAND, so which is the AND. Okay. So, I'm just defining it formally. Why? It's kind of to be consistent with what we did for circuits. For circuits, we said, okay, NAND gate was the only thing that we needed. For quantum circuits, as we will see, you need QNAND and Hadamard. Okay. We'll get there in a second. But let me first define it formally and then we'll see. So what does this gate correspond to? Well, you check what happens on each basis vector. If I send in 0, 0, 0, what should you get out? So 3 photons now. We have the first photon in state 0, the second photon in state 0, the third one is also in state 0. What would you get out? You can calculate what is the NAND or not of the AND of the first two things. 0, 0, it's 1. So you would get 0, 0, 1. Okay. So maybe let me draw the picture more clearly. So QNAND is something that operates on 3 qubits. Okay, and I can describe what it does by describing what it does on all the 8 possibilities. So if you have maybe 1, 0, 0, it's going to be 1, 0, 1. If you have 0, 1, 0, it's going to be 0, 1, 1. 1, 1, 0, it's going to be 1, 1. Okay, you can then complete out the picture. I'm being lazy. I have to write down all 8. Okay, so this is what QNAND does. The action on the basis vectors. If I have you describe it on general state, you would just add up all these equations. Yeah. 1, 1, 0. So what is a Q? So NAND of 1, 1 should be, oh, that should be 0. Thank you. Thanks. Okay. This is another gate. It's operating on 3 qubits, but it's a gate, so it is what it is. Any questions? Yeah.
Wait, does that mean the input for 111 should also be 110?
Oh, sorry. No, I think this is correct. This is fine. Yeah.
Is there like a standard ordering for
Not really. Yeah, I don't think there's a standard ordering. You just have to use whatever is convenient. Like here, flipping the third bit is very convenient to write down because somehow it's more consistent each time. Okay. The order doesn't really kind of change much. All right. So now we can define quantum circuits, all right? And let's just revisit what classical circuits were. And then now that we have gates, we'll kind of use the same convention that we had for circuits and just replace the gates with quantum gates. Okay. So here's what we've been waiting for. So first, recall. So remember we had this, like Boolean circuits, right? We had x1, you could have x2 up to some n variables. And you could send it through all kinds of gates. Like, let's say we only use NAND gates. We said that's enough. And so on. And then we said, okay, maybe some of these gates will be labeled with output things. Right, this was our model of a circuit. And when it comes to quantum circuits, it will be the same thing, but we'll replace the NAND gates with the Q NAND gates, and we will allow Hadamard gates. Okay, that's the change. It's almost the only change, but there's one very critical restriction for quantum circuits. Okay, so let me say Q circuits replace gates with quantum gates. Okay, but when you're designing this or writing down this quantum circuits, you need to have each gate has only one number of incoming edges. Okay, so in the classical world, we could have the same nodes output point to different gates, right? We could reuse the variables multiple times. Like for example, this was fine. I could send this NAND here and here. In quantum, that is not allowed. Okay, so you are only going to use each one once. And this is, again, it's a restriction that comes from physics. There's something called no cloning, where you cannot just duplicate a system for free. Okay, but mathematically it just means that we have a stronger structure on what we allow. Okay, so pictorially it's going to be something like this, and then I'll tell you. So you can imagine I have my input kind of loaded in as initial states. Think of them as photons. I have n photons. If I'm working on n bits or n qubits now, they all go through this giant thing, and I might have, like, let's say, a QNAND here. They come out, and maybe once this wire comes out here, I'll put the Hadamard gate. These go through, and maybe I had X4. This comes here, and then I'll put a QNAND on all of these three things. Okay, maybe I'll put a Hadamard, maybe a Hadamard again. And then I can do whatever, right? I just chain them however which way I want. Okay, and in the end, all the photons go through, right? What's the output? How many ever qubits you enter, that many qubits you will have as output. Okay, and in the end, whatever comes out, whatever you have n photons, you made them run through this obstacle course with this, this mirrors or whatever, however you're implementing this NAND and so on. You have everything there, and then you do the measurements. Some m of these registers or m of these photons you will measure and call them y1, y2, yn. right? So all the measurements are pushed to the end. You get out this n photons in whatever thing that you have. You would like to measure some subset of them and say the outcome of the first thing is like bit 1 of my function, bit 2, and so on. Okay, that's kind of a pictorial description. And we can also define it formally now. It's a mouthful, and there are some important quirks. Okay, so in quantum computing or quantum circuits, there's this notion of working memory when we think of algorithms, right? You know, you think of any algorithm you write, you can create new variables anytime in the program, right? If you think of a quantum computer, memory is actually like, you know, it's actual photon, okay? The same thing in circuits. So since you cannot rewire, you know, I can't just copy something easily, you have to account for the number of photons that you're going to use in the working space ahead of time. So a quantum circuit on QNAND and Hadamard basis. Okay, you know, just QNAND and Hadamard are enough to simulate all possible gates. We had something similar in classical world. NAND was a universal operation. Something similar is true in the quantum world, but you need to allow Hadamard. Okay. On n plus a qubits. So you should think of n as number of variables and a as working memory. Okay, physicists use the term ancillar qubits, meaning extra things that you're adding, ancillar registers, or I would think of it as just like extra memory that I'm creating, but I have to declare ahead of time. Okay, is a sequence of gates. You're just going to apply a sequence of gates one after the other. So the description of the circuit is what is the sequence of gates. So it will say something like, okay, gate 1, gate 2, up to gate S, where S corresponds to size of the circuit. So I have S gates, and each gate is either like, you know, okay, apply not on ith photon, okay, or you know, it'll say apply QNAND on IJK. Okay, so each gate is either, sorry, not, it's not, it's Hadamard. Okay, some register and say, okay, apply Hadamard there, or you pick some 3 things and say apply QNAND there, and then so on. Okay, any questions? So that's the definition, and the evolution of quantum circuit is something that we already saw. So you start with some initial state psi0, yeah?
Does each input, like you have x1 all the way to xn, each of those have to correspond like straight out to a y1, or can you?
No, yeah, so I'll tell that in a second. So, I mean, so this is how the evolution is going to go, and then we'll say how it corresponds to an actual function here. Okay, it's a good question. So we have some state psi0 that we put in, and we can calculate, you know, we can see how the system evolves when it do implement it physically, right? It goes through psi1, you know, apply first gate. Then it goes to psi2, apply second gate, and so on. And then finally, you'll have some final state. Okay. So you should really think like, I have this sort of obstacle course, I'm sending some photons in and some photons come out. The same number of photons come out, but they're in some completely different state as dictated by this evolution. And this is something that we can implement physically. And presumably we cannot simulate classically. All right, any questions about this definition? We have all the ingredients to do it if you had to compute it. Like if I give you a gate, circuit with 10 gates, then you can maybe painstakingly just compute what happens on each of the basis vectors, 2 to the 10 things, and then figure out the output and write it down if you want. Okay, but we don't have to. We just know that this is the definition mathematically. Yeah.
What exactly do the memory bits correspond to?
It's like additional photons that you're adding in.
Like, what would you?
So the gates can overlap those working memory things too.
So when you're adding something in, is that like you have like a constant?
No. So maybe let me draw a different picture. So basically this circuit, okay, so I just defined what a circuit is, but let's see what it means to compute a function using the circuit. Okay, maybe that will make it clear. Okay, so we'll say a quantum circuit on n plus a qubits computes a function or usual functions, like, I want to compute, let's say, the XOR of the bits, or multiply the numbers, or factor the numbers, or something like that. If the following holds. The circuit diagram is something like this, and I have my circuit, and I know exactly what it does on, I don't know what it does, but what it does is physically determined, right? How the state evolution goes. If I send in n plus a photons, they come out as n plus a photons in some other state. So what we're going to do is send in the initial state, which is the first n photons are initialized according to my input. The ancillas are initialized to zeros. Okay, so I'm sending photons, I'm encoding the input x as the states of the n photons, and then I have the extra ancillas. They're all going through this obstacle course, and I get out some things here. All right, I get out n plus a wires. Out of these, I now measure some m of them. You can also, just say I'm going to measure the first m. That's also fine. It doesn't change anything. You'll get some number now, some bit y1, y2, y3 up to yn. Okay. So the measurements introduce randomness, right? And if I'm in state plus, we know that if I measure under the 0 on basis, I'll get half the probability. I'll get 0 with probability half and 1 with probability half. So the state, whatever you are in here, determines what are the outcomes of these measurements. Okay. So you do the evolution of the circuit, just compute the final, or the state goes through, and then you have the measurements, and we'll say it computes if when I do this physical process, the probability that the measurement readouts agree with the true function output for all of the m coordinates is at least 0.9. So if this holds, then we say that the quantum circuit computes the function. Okay, you specify some number of bits n, then there's a quantum circuit, it has some extra ancillas. The reason we need it here, we didn't need it in the classical world, is in classical world, duplicating information is for free. Here, information is like an actual, photon, so you can't just pull it out of thin air. So you kind of allocate them ahead of time. Okay. Any questions about the definition? Yeah. Yeah, there's nothing special about 0.9. You can make it any constant which is better than something, and you can boost it. You can make it very like exponentially close as well without too much cost. Yeah.
So do you not actually need the ancilla? Is it just for like?
We need them. You need them. You need the extra memory. Like it's as if saying that maybe for some algorithms need extra memory instead of just the n bits, right? You have the input, but then you also need some extra memory, right? But as in quantum computers, memory is an actual photon, so you just had to put them in first. Okay, so all of this, really think of it as a physical experiment you're doing. I put this n+a photons, make them run through this obstacle course, do the measurements. 90% of the time, I'm going to compute the answer to F. All right, yeah. It is considered computable by physical means. I mean, you can actually show that, you can simulate quantum computers on a Turing machine. It would be inefficient, but it is possible. And, it's a challenge to, but, as I said, nature gave us this amazing power. Then we have a model now, and we have to see what it can give us. Yeah.
So the statement is saying that, like given this sort of function, like there exists like a
Oh, so we are saying a function f is computed by a quantum circuit if this holds. Like, I have a function that I'm trying to compute, and then I have a circuit which I have which computes that function. Yeah, exactly. It's like a definition, right? So we say a quantum circuit C on an n+a q bits computes a function f if this holds.
If it's just like the statement of the number of input.
This is true, and the circuit does this, right? I have the circuit, I feed in x1 through xn and zeros in the ancillas, I get the output states, I measure, and then the y has satisfied this equality. Okay.
Like the bits or the qubits, probability, like the accuracy.
Yeah, the accuracy should hold. So once I do the measurements, I actually have bits, because things collapse and so on. So we are doing the measurements in the very end. Until then, everything is qubits. Once I do the measurements, things collapse. Yeah.
Regarding simulating on Turing machines, right? Like today, we have GPUs that can do an unbelievable amount of linear algebra. Why, like, this is a super useful model, but why do we need a physical quantum computer?
That's an excellent question. I would say, there's a bad way to answer it and there's a good way to answer it. The bad way is to say that if I have k qubits, then it's like doing linear algebra 2 to the k numbers. So even if it's k is like 100, you're already at like 2 to the 100, which is humongous. Okay, but that, I think, that's something that you see a lot in popular science, which I don't like. There's Scott Aronson, who is a famous and well-known quantum complexity theorist, and he has a pretty popular blog. And the tagline is, if you take nothing else from this blog, quantum computers won't solve hard problems instantly by just trying all solutions in parallel. So the point is that even though they have 2 to the k numbers in it, okay, it's not as if you can access all of them at once. There's a cost. The implicit limitation of the power that nature gave us is we kind of get to use this device only once. Once you do a measurement, things collapse. Okay, so there's a lot of information inside the state, but we don't know what it is until you measure. But once you measure, things collapse. Okay, So, you often see people say, oh, they can try exponential number of things. They have that exponential number of things inside, but you don't know it until you probe it. And once you probe it, you lose that. Okay. So that's the model. It's a very concrete model. The question is, what are they good for? Okay. So by and large, I would say the most famous sort of application is the following. And this is the theorem due to Shor in 92. Even before the first CNOT gate was actually physically realized, someone showed that there exists a O of n squared size quantum circuit to factor n-bit numbers. If you give an n-bit number, I mean, there is a quantum circuit with exactly n squared gates. I mean, it's pretty efficient. If you think of classically, if I have something with only n squared gates, then I can just implement it very fast, right? But in quantum world, physical is hard to do. But amazingly, it can factor numbers with only n squared gates. Right? So I give you an n-bit number, then the output of this quantum circuit will be the prime factors. And the number of gates is only n squared. To kind of put this in context, there's this RSA challenge where it's like open to everybody. You can use how much of your hardware, they have a set of numbers that you have to factor. That's it. And the most successful challenge, is like in 2020, someone factored an 850-bit number. And that involved like gazillion amounts of computation on a classical computer. Okay. But if you had a quantum computer, it's as if you're just working with 850-bit numbers. I only need 850 squared gates. It should be easy. But the point is, we are still not there physically building these devices. Okay. Even doing 2 or 3 qubit states is quite non-trivial. We are seeing amazing progress physically realizing these things, but we are kind of still, well behind. Okay. Any questions? I mean, the point of these 3 lectures was to just say and give you the full description of the model. How to use it, of course, is a different story. So we have the model. If you could build the CNOT gates, Q9 gates, we had the circuit that's Shor wrote down. It's mathematically written up somewhere. You just had to put that on a chip and be done with it. Okay. Any questions about this? Yeah.
How do you deal with the non-determinism of the output?
Oh, it's all in probability, right? So I wouldn't say it's not non-deterministic, but it's randomized. So you will be correct 90% of the time. Okay, and those are odds that I'm okay with.
So you're designing your circuit in such a way.
Yeah. Okay. Any other questions? Yeah.
Like in practice, like people run the circuit many times.
Exactly. Like, this 90% is arbitrary. You can, once I get it for 90%, I kind of do it 10 times and it becomes like 99%. If I do it, a few more times, then it becomes 99.99% and so on. It's like really easy to boost the accuracy. Any other questions? All right, if there are no other questions, thanks everyone. I'll see you on Tuesday, December 6th.